Sherry had it planned out.
Oh, for real? Not much of it.
She's all out of whack.
What? But doesn't it come?
I'm like, oh, that's just.
Isn't me one of the two on top? Yep. Yeah. And then on top of this, and then yeah, I already said. Yeah. What kind of lifting?
We can use broken.
Really? And this one. It breaks easily.
Morning. So did you guys all make it to the Pride event yesterday for that extra credit?
They have tie-dye, no.
Or went to I know they didn't have tie-dye. I was kind of disappointed, you know? I got my nails did, you know,
Nice.
although it's all coming off now, but you know. Got my face painted, you know. so. Put these quiz up on the board.
Oh, yeah. But it's not always like that. Yeah, probably still.
They were all-
What kind of people are?
Start chipping off. So.
I know. He's like, I can never make it to 10 minutes.
No, I was from last time
You know, polish?
and I was like, I think I'll see him. There's a lot of sits here. Like 7:30, so like by the time I go by last grade, like drunk, it was like 7:40. Okay. I should go. I'm not gonna go freaking that late. I was happy.
I should say, have you
But it was
used
going
nail
down on
polish?
the road. USA. My dad was housing just going up a little hill. But then I had to go slow because it was really hard. No, I couldn't because it was like one of the other cars. So the person was the hospital.
Look at the names on the box.
So I was asking about so okay, I phosphate, tetrahydride, and it just adds up. No, because it's changing. Well,
I would just do like for the what I am.
But you just got the numbers. Like a year was on dry. But there's something that kind of Oh, yeah, what it is? Because it right there has that hydroxide or phosphide. Did you get one?
One, I'm gonna iron. I put two.
Oh,
I put two. But iron phosphate, tetrahydride is out of fourth of each three. And then it's like
Right down the street.
Or H2O. This was off the hydrogen. And it's Fe, not ion.
Oh, wait a minute. Never been
Wait, guys, for using the phosphate, it says right here that the charge is -3, and then
Of course, I knew that was gonna happen. That was just.
Sometimes I'll come home from work and see Hannah. She was laying in the bed.
Oh.
Six hundred.
yeah, yeah, that's what I said. Oh, A.
Oh, wait, that's a. Well, obviously, my Kaiser.
But it wouldn't.
So he'll chase her and then she'll chase him. And then just go back and forth.
They'll wake her up.
So that's not for.
And they'll be fine. But since they're like.
You're right. I put the iron. And you put two. Yeah, one state.
She'll start barking because she's like, there's someone there.
Yeah, and then that's just gonna be through.
And we're over here like.
Because the charges I have like.
Oh, no. Wait.
Chloride.
Oh, it's a huge.
Oh.
It's funny, but it's funny, there's one like next to us.
So we're just gonna do changes and then. Did you go up phosphate?
Phosphate, yeah, and then just hydrate.
Yeah, so it's not just at the end of it. Before each one.
Yeah.
Jennifer, can you see the quiz?
What was that? Yeah.
Yeah.
I think we've done all.
Chloride acid.
So I think you did write it.
I'm not down with the last one. They said that they have a big digits.
Okay. Everybody got it? You guys are ready? I can give you a spot to submit it on. You're not ready?
Go the numbers down. For what?
Well, not really, I mean, I just changed the name because it doesn't match the equation. But I don't know what the, I forgot what it was for.
I think you said that. It doesn't, I think we've done this one before too.
It's like exactly kind of like.
Or just a number.
Could we choose something not the, or at least try? I did it right. Say phosphorus, I know. 10. 4, and then oxygen.
Yeah, because I would have to choose.
You choose it.
Thank you.
You got out or? You- when you- Separate that. Alright, so she finished early. I know that. What do you want to do? But like back to the summer.
It just got really messy.
Oh, you're all white, that's fine. Take us there. Gotta get down this way. Yeah, I couldn't. I go like that. And then when it says drying up, that's when I say. I can read it down. You can look, I like the shows. Yeah. You can look, I like the shows. You can look. You can look. You don't put the phone on. You should say like he doesn't. You put lotion. Lotion. You know, smelling. Do you make sure that your hairs are like calm down? No. No, you had it. Boy, I don't even know how much you get. Skinny or alright. Like split up. Just little bit. También. I love this stuff. I think it's just one of the.
Dr. Henry, so for our grade,
Yeah.
is like, what we got on the test already reflecting on there, or is it?
No, it isn't. It's gonna change.
Oh, damn.
That's just extra work.
It's just extra.
What
You're
is that
okay with it.
possible?
You're like, yeah, just
So
leave
you're
it
seeing
there.
it like that, it's
Oh,
nice.
okay.
Sometimes we're gonna
You know, you don't want to give me any extra work.
because that, I think it's just graded the choice and it's going to grade like the stuff that we typed in.
All that extra credit, it adds up real quick, doesn't it?
So I wrote it on my paper, and I wrote a note too. Well, it, oh, that, or that's just clicking on it, so that's why I'm gonna do that, but it's really down there. I have some. The one with Bay lazy, I don't think so. Because the one that was gonna go to Fireball with Bay, I was like,
Oh, it's not, I see what it's saying.
I'm like, oh, they're rubbing them.
I know.
And like, it's just worse, like, peel it so you get.
Okay, try submitting it now.
Actually, if I want to make pasta, if I do, you try, let me try. I go half. And this, it keeps off. I'll let you look at it, but actually it looks good with the torch, but then it's like off. So you just see. Yours is more bright. That's nasty, I'm sorry. It's with chocolate. It's with all those.
Okay, so you said like,
Oh,
well,
sorry.
so like. Property.
The water. The water. Oh, you sent me?
No,
I saw that one, but no, it's like the tool that they use. You went to.
It's always good
She
to be
just told me
safe.
about it.
Yeah.
I'm sorry.
No, what was it? I drew, or I forget to ask for it. She's like, I want to do that. So, wait, she's like, put her on one page. Oh, that's what I told you. And she showed me back again. I think it was before we. I think the little. Oh, thank you. Why was Oh, is it?
Yes.
Yeah, I've seen that one también. Like, go through my feed. And you're just like, this one. See? So how much on TikTok? Did she start to send me?
I like it having the guys better.
I feel like it might be a good thing. Really, it's a while to download some pieces. No, I just want you to. Yes, from TikTok. No, that's right. But like it was like in those.
Both, like,
Oh.
She was and I would have a something that's what she sends me today. That would watch.
And if I was gonna send this, I was like. Only two people don't. Oh, yeah, I did like a little one.
I just wanted to take pictures. I'm strawberries. Oh, yeah, the thing.
Okay, well, yeah, so I took them over there. And my sister put it with go to Jumbo Juice.
Bro.
To get one.
No, not anymore. We have it in Zoom. 30 minutes or the whole class.
Okay, everybody uploaded their quiz?
Oh, shoot.
You guys want to go through it? Set up with it? Okay, so what is wrong with A? Name is wrong. Okay. What is it? Okay, so why is the name? Diphosphate. And then how is the formula? You saw that?
Yeah. Why did we?
Because. Compound, remember, compound uses right? So, but there are those exceptions, because you guys remember, if you look at the polyatomic ion, I. Which is H2. Fluorine. Now this works out in this case because it's covalently bonded together. I have. That's. Okay, what about the next one?
What the heck? We made 3?
Formula looks wrong. Okay.
Supposed to be Fe.
It's supposed to be Fe. Anything else?
Yeah. Charges on function.
Everywhere. So I got this from my girlfriend's son. He was working on a chemical equation. So he's working on balance. And he does this, and I always get on it. You can't do that. You have to write it below. He's like, well, why? And I'm like, that's the rule.
So then wouldn't it be the same on top as well? F3PO4 2? Right?
F3.
On for A, wouldn't it be the same? Because it's iron phosphate.
Yes, this is iron.
Okay.
This is iron too. Remember, I told you they can have different charges.
Okay.
What about? Yeah. Okay. And what about this one here? Right. That's your.
A little bit, a little bit.
Okay, piece of cake, not too hard. Are you feeling confident about nomenclature?
I can't even pronounce the word.
Nomenclature? Means name. Nomenclature. Name. Okay, so I can erase this. Everybody's good?
Yeah.
You guys ready to move forward?
Yeah.
Good. Okay, so normally I would go through chapter 11. We're going to go to chapter 8, which you guys have already done. It's just balancing chemical equations, but there's a little added on. So now that you know how to do inorganic nomenclature. Solid nomenclature. Chapter 8 is going to be then we'll go back to So we were also supposed to do a special lab today. Unfortunately, you guys are not going to make fireworks this week. You may get it next week, or we're trying to get it before the 4th of July. But the chemicals that I ordered got canceled because they were so back ordered. So, hopefully they'll be here next week. So you guys will get to celebrate finishing the passing this class. That's cool. What was that? That you guys are gonna make? You're just gonna make sparklers. I can't have you guys make anything that's crazy.
Really expensive.
What I'll do is next year is like for my general chem, I may have them do something that's pretty spectacular.
That's nice.
An incentive to take general chem. You'll be there?
No, hopefully not.
You guys know you're loving it. By the way, how are you guys feeling about chemistry so far? Anybody ready to change their major?
Yeah.
It is still love hate.
I think so, yeah.
It's summer is always interesting because it goes so fast and you're just like boom, 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 boom. So it is. It's really a love hate type of thing. I told you. I said if it were me, I would not take this class.
No, I was always told not to, but I was like,
Yeah.
I like the back.
it works for some people, you know. I like my classes going fast, but just going all along. Okay. So you guys have the handout for chapter 8?
Yes.
Okay. Guys can see it. So you guys are just getting into the class, you're just starting to get types of reactions or reactions in general. So what are one ways that we can determine if a chemical reaction has occurred? Has occurred. A chemical reaction has occurred. Not a physical reaction, but a chemical reaction.
Oh, when it changes.
Okay, but more specifically, what are ways that we can say, oh, yeah, that is definitely a chemical reaction? Okay, so that's again really general. You want to be more specific. So what is it that we observe that we could say? What aspects of it? Talk about. Oh, so what is endothermic? What was that? Somebody said over here? So you're saying heat is being trapped, or you're generating heat. Is that what you're saying? Okay, so heat is a form of energy, right? We can agree to that. And also, by getting heat generated, that also tells us that a chemical reaction has occurred, right? So when a log is burning, that is a chemical reaction, right? Everybody agrees?
Yes.
So have you guys ever ran into walls or anything like that before? Had a really crazy night out, and you have to use one of those cold packs, you know, put on your head to get the swamp from getting too big. Right? So that cold pack is also an example of heat being transferred, right? Or heat being stored in space, so then it's getting colder, right? So that's another example of a chemical reaction, right? So just the fact that we're either absorbing heat or releasing heat gives us an example of a chemical reaction. Okay, so what else? What was that? You said a change of color? A change of color, right? If it changes color, you know, it starts off pink and it turns green, fluorescent green. That's a sign of a chemical reaction, right? Okay, what else?
Formation of a solid product.
Formation of a solid product. He's really good at reading the slides. Huh? Formation of a solid product. You just know this, right? Okay, formation of a solid product. So when we have two chemicals that are clear liquids, then all of a sudden it gets all nice and cloudy, and then it just starts to drop down at the bottom, and then you get this little pellet form. That's an example of a chemical reaction, right? Okay. Oh, what else? Come on, go ahead, finish reading.
Formation of a gas product.
Formation of a gas. Plop, plop, fizz, fizz. Oh, what a relief it is. All right. You guys have to use Pepto-Bismol, not Pepto-Bismol, Alka-Seltzer? Yeah, Alka-Seltzer. You never use Alka-Seltzer? Where you see bubbles starting to form up and everything like that. Oh, you're missing out. Best thing ever, especially when you had way too much to drink, let me tell you. So that's an example of a chemical reaction, right? You big gas. What else? What else?
Emission of light.
Emission of light. Hey, right? Glow sticks, we pop them, they start glowing, right?
Or fireworks.
Fireworks, yeah. Glow stick, exactly. Okay, so those are ways that we can determine that we have a chemical reaction. That's evidence. Right? So here's an example of a color change. So this is potassium permanganate. Potassium permanganate actually starts out clear, when we start adding to another reaction, and it'll actually cycle, it'll turn a nice little purple color as the time continues, it'll actually go back to that clear state. Right? So it's actually transferring or oscillating in this type of reaction. This is an example of a formation of a solid. So this one is sodium chloride added to silver nitrate. So basically get silver chloride being formed. Forms a solid, so that she starts clouding up and then eventually it'll form a pellet. Alka-Seltzer, right? So basically you get a release of, in this case, it would be carbon dioxide that is going to be added. So heat or light. Right? So this is thermite basically ignited. Addition of light. Heat transfer. So heat transfer could be the presence of a physical change, but it also could be the presence of a chemical change, right? So I gave you the example of the coal pack where you snap it open, it gets really cold, right? So two things are happening. One thing is the thing is going to absorb, right? The other thing is that you're going from hot to cold, right? So now that you know how to name chemical compounds, we're going to use this to sit there and write chemical equations. So if we guys take a look. Okay, it says when solid sodium is added to liquid water, a reaction occurs producing hydrogen gas, sodium hydroxide solution, and heat. So how would I write this as a chemical equation? Okay, so what are my reactants? Okay, so what is the chemical symbol for sodium? And you said water. What is the chemical symbol for water? And that's going to make. So what is the symbol for hydrogen gas? Hydrogen gas.
H2.
H2. So because we know that hydrogen is all by itself is what? It's an acid? Are you sure? Hydrogen all by itself is an acid. It's a gas and it's What was that? It's an element, but it's H2. Why is it H2? Nope. About it, we talked about it the very first week of class.
Diatomic?
That's right, it's diatomic. What does diatomic mean again? Two, right? There's two of them. So what are our diatomic elements? Hydrogen, obviously. Oxygen,
Chlorine,
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 bromine,
bromine,
iodine,
iodine, and nitrogen. That's right. Have no fear of ice cold beer, right? Remember that? Obviously you didn't. Okay, put that one on the quiz, huh? Okay, and what else are we making? Sodium hydroxide. So what is the chemical formula for sodium hydroxide? Chemical formula for sodium hydroxide. NaOH. Right. And heat. So for right now, we're just going to write plus heat. Although you guys do know how to calculate that. Okay, is it balanced?
No.
No, it's not balanced. What do I need to do to balance it? You put my elements?
Yeah.
Okay, so what do I have? I have Na, H, and O. So how many NAs? I have one Na. Okay. And then on the product side? One. Okay. How many H's do I have?
and then 3 on the other side.
Okay. And oxygens? Okay, so we know that that's definitely not balanced, right? Okay, so what do I need to do to balance it?
Add 2.
Add a 2 in front of the NA.
Yeah.
Okay, so we put a 2 here. Okay, so then that gives me 2 NAs on one side. I need 2 to, yeah, okay. So then that gives me 2 NAs on both sides. How many hydrogens do I have now? I have 4 total. And then how many oxygens do I have? 2. Is that balanced?
Add 2 on H2O.
And then add a 2 on H2O.
Yeah.
Is that balanced? Okay, piece of cake?
Yeah.
Okay, good. Move forward, everybody got it down?
Yeah.
Okay. So here's our chemical equation. Now we're gonna add on S for solid, L for liquid, G for gas. AQ is for aqueous. So anytime that you see the term solution, it refers to aqueous. Okay. So we need to start including this in terms of our chemical reactions to help us understand what we're working with. Okay. You guys already have this balance, so let's keep moving forward. Okay, so S is for solid, L is for liquid, G is for gas, and AQ is for aqueous. Aqueous basically means it's in water. Solutions, anytime it's a solution, unless they say otherwise, it's in water. Okay, do's and don'ts. You guys already know do's and don'ts. What are some of our do's? Do balance the chemical equation using what? Coefficients. Okay, don'ts. Can you change the chemical formula? Can I just make up elements and chemical species and stuff like that and just put them in there just because I want to? Okay, you guys already understand what the arrow means, right? So you know that on the right-hand side, it's the product. Then on the left-hand side, it's the gas. Okay, let's skip over this because you guys already know the steps. Got it? Okay, let's get to the meat potatoes of it. So it says balance the equation for the reaction of solid phosphorus pentachloride. Phosphorus is pentachloride with liquid water, yielding aqueous solutions of phosphoric acid and hydrochloric acid. Okay, so what are my reactants? Okay, so what is the chemical formula for phosphorus chloride? Pentachloride. Anything else that we have to add? You said plus H2O. Anything else that I need to add to that? What is it? Is it solid, liquid, or gas?
Oh, yeah, okay, so.
Okay, so it's solid.
Solid.
That's right. One compound, that's a solid, yes. So, and then,
So if it is showing, how we know if it's solid or gas? How we able to identify it? Whether we have to-
does it tell you?
will it always tell us? Like
In
that?
most cases, it'll tell you, but there's certain things that are clearly gases, like oxygen, nitrogen, chlorine. Okay. And then there are other things that are clearly solids, like sulfur. So just by what your exposure is.
Okay.
And if it's a metal, except for a metal, it's going to always be a solid except for mercury. Mercury is the only metal that is a liquid. Okay, so is water, solid, liquid, or gas? Okay, and that's gonna yield. What are we making? What are we making?
Phosphoric acid.
Okay, so what is the chemical symbol for phosphoric acid?
H3PO4.
H3PO4.
AQ.
That's right. Okay. That's what? Chlorine?
Hydrochloric acid.
Is
HCl.
chlorine and hydrochloric acid the same thing? HCl. Am I forgetting anything?
AQ.
AQ. Is it balanced? Okay, so how do I balance it? How many hydrogens do I have on the reactant side? On the product side? Okay, how many phosphorus? How many chlorines on the reactant side? On the product side? How many oxygens on the reactant side? And on the product side? Is it balanced? Okay, what do I need to do to balance it? How many oxygens do I have? And how many do I need to have? Okay, so how can I make that happen? On the reactant side? So then that gives me 4 oxygens. How many hydrogens? 8. Okay. How many CLs do I have?
5.
I have 5. How on one side and on the other side I have how many?
1.
So how can I make it so it's 5 on both sides?
You could put 5 in front of the HCl.
5 here. Okay, how many hydrogens do I have? Is that balanced? Okay, piece of cake? Yeah, we've been doing this since day 1, right? Now we're putting it all together. Now you guys are starting to see where I mean with it's building up. So. Can I go ahead and erase it, move forward? Everybody got it down? It's like, you know, if you miss, like a couple of lectures, you're screwed, right? You're not gonna read. Okay, so we've talked about the particulate level, and we've also talked about the molar level, the concept of whether we have a half or not. Okay, and we've kind of talked about it briefly. Like, remember I told you I can't cut you in half because if I cut you in half, you're cutting that molecule. So that's on a particular level. If I only have one oxygen, I can't cut it in half, right? So, but if I have a whole bunch of them, then you know I can take half the oxygens that I have, right? And then so, and that's all this is saying. Okay, and you guys already know how to interpret what a reaction means, right? So this tells us that we have two hydrogens, right? And one oxygen. That's what that chemical reaction shows us. And then that means that we get two wires. So this is that concept of having a large quantity of it, right? So I have half a dozen, I mean, if I have a dozen of hydrogens, I only need 1 dozen of oxygens, and that's going to give us 2 doses. Well, now that's going to be the same case of moles. If I have 2 moles of hydrogen, I'm going to need how many moles of oxygen? Based upon this chemical equation. If I have 2 moles of hydrogen, how many moles of oxygen am I going to need to make 2 moles of water? 4. Going to need 1, right? So it doesn't matter how I, you know, if I use single molecules. You guys remember what a mole is?
I wrote it down.
A mole equals 6.022 times
6.022 times 10 to the 28.
Okay. You guys got that? Okay, so let's talk about the types of chemical reactions. Okay. So there are basically 5 types of chemical reactions that we have. Basically 5. Okay. They can fall into these 5 categories. That's right. So very first type is called a combination reaction, or we call it a synthesis reaction. So it's where you take one compound or element with another compound or element, and you add them together and they make a single new compound. Okay. So A plus X yields AX. Okay. Write the equation for the combination of solid aluminum plus gaseous oxygen to form solid aluminum oxide. Okay, so solid aluminum. What is the chemical symbol for solid aluminum? Okay, ALS, AL parentheses S, plus, what is the symbol for gaseous oxygen? 2 with the parentheses G. That's going to yield what is the chemical symbol for aluminum oxide? Al2O3. Solid. Okay, is that balanced? Okay, what do I need to do to balance it? How many aluminums do I have on my product side? On my product side? I have 2 less speed. And then on my reactant side, how many do I have? How many oxygens do I have on my reactant side? And on my product side? Okay. So clearly it's not balanced. So what do I need to do to balance it? I need to put a 4.
On the reactive side, and then put 2 on that side.
So put a 2.
Yeah.
2 here. Okay, so if I put a 2 here, that gives me a total of 4. Okay. And 6 oxygens. Okay. So I need to put a 3 there. 3 on oxygen. And 4 on aluminum. Okay, piece of cake?
Yep.
Yes, if you have something that's charges, you have to count it. If it's left as charges. Okay, so we have a decomposition reaction, like decomposing bodies. So basically you have something that's together and it's going to be broken down into 2 or more substances. Okay, so we have AX being broken down to A plus X. So water decomposes into its element when electrical energy is added. Okay, so how would I write the chemical formula for that? H2O. H2O with a liquid. That is correct, not a Q, because that means a substance. And that's going to yield H2 plus O2 gas. Is that balanced? Okay, so how do I balance it? Okay, so that would be 4, 4, 2. Okay, questions? Cash. Okay, so usually if we have energy that's being added, we can put a change here. That's usually mean heat, or in this case, it'd be electrical energy. So we just put electron, or we put just electric on top. Not a positive side. Is the electron a positive side? Right, that's right. Yeah, or you put delta and then subscript. So then that tells you it's electrical. Or you could just write electrode. Okay, so certain reactions are reversible. Basically meaning that they can go both directions. Okay? Now, when reactions are reversible, they reach what we call an equilibrium. If they're reversible in the same container, meaning that one is going in one direction, one is going in the other direction, they reach what a point of equilibrium. Equilibrium is kind of like a point where the rate where one is going in one direction and the rate where the other one is going in the other direction are going to be equal. It doesn't mean that they're going to have the same amount. Okay, it just means that the rate is equal. The event itself becomes an equal event. Okay, we'll talk more about that later on. So, as I said, equilibrium, and this is how you write that. You have an arrow going in both directions, or you'll see an arrow drawn like this. Okay. So we have a single replacement reaction. So this is where you have one element that's going to be replacing another element in the compound. The way I like to look at it is you're replacing the old girlfriend with the new girlfriend. So in this case, A is going to be replacing B. So now we have AX. Okay. So that's a single replacement reaction. Now, these reactions are also often referred to, or can be, what we call an oxidation reaction, oxidation reduction reaction. So oxidation and reduction basically means that electrons are going to be transferred. Okay, so if something is oxidized, that means that electrons loss of electrons. Okay. The way I remember this is loss of electrons, oxidation. So, Leo, and then ID electrons. So reduction. And that's perfect. Okay, so loss of electrons, oxidation. Gain of electrons. I'll show you an example of that in a second. Okay, so when the element is a metal, it's going to replace a metal, or it's going to replace hydrogen, okay, in the compound. So if you have a element that's a metal, it's going to replace another metal in the compound. Okay, if the element is a non-metal, it's going to replace a non-metal in the compound. Okay. Don't sleep on me yet. Let me give you an example. Copper reacts with a solution of silver nitrate, right? And equation for the reaction. Okay, so copper. So what is the chemical symbol for copper? U. Is that going to be solid, liquid, or gas? And it's reacting with what? So what is the symbol for silver nitrate? Chemical symbol, formula for silver nitrate? Ag and nitrate. NO3. And it's a solid liquid gas or solution. So how do we write solution? Ag. And that's going to make who's replacing who in this case? That silver nitrate is replacing who? Okay, so is silver nitrate replacing copper? Copper is replacing, wait, say that again? So it's gonna, we're gonna have copper nitrate. So in this case, copper is gonna be replacing the silver. Now, copper, when you have a replacement, a single replacement reaction that occurs, right? It will make a copper 2+ ion. Okay, so then how many nitrates do I need to balance out that 2+? I will need 2. So I'll write it as now I'll tell you, most transitional metals, when you have a single replacement occurring, it's going to always be a 2+, except for aluminum, which is always going to be +3. And we know that silver is always going to be a +1. Cadmium is always going to be a +1 in a single replacement reaction. Okay. And then we'll get silver by itself. Is that going to be a solid, liquid, gas, or aqueous? Okay, is it balanced?
No.
No. Okay, so what do I need to do to balance it? Ag going on there. Yeah, nitrates. And we have okay, so our Ag, how many Ags do we have
In this case.
on the reactant side? What? On the product side? How many nitrates? 1. And then on the product side?
Oh, wait, 6? 2.
2. Because you're looking at it as a solid unit. Okay,
Oh.
You don't multiply 3 times
I
2.
didn't see that.
That's what
no, because we're looking at the nitrate as a single unit.
Okay.
We're looking at NO by itself, right? Yeah, I'm sorry, NO3 by
Yeah,
itself,
great.
right? And then over here, it tells us, because that parentheses lets us know that there's 2 of them, right?
For copper 1 and 2.
Is it 1 and 2? Or is it just copper 1?
1.
Okay, so then you said we put a 2 where? Here. Okay, so then that gives us 2 silvers. You know. Okay. Okay, does that help?
Thank you.
Questions?
Are we using basically like this last electron?
Oh, we're getting there. You can just bear with me first, sir. Okay, everybody got it balanced. You're good with it being balanced. Okay, so if we take a look at the copper, right? Copper by itself. The charge on copper on any element, right, is going to be what? It's going to be neutral. Neutral means it has what charge? No charge. Okay, so I'm going to write a big old 0 on top. Okay, now this copper that's in the copper nitrate, what is going to be the charge of it? It's going to be a +2, right? So if it's going to be a +2, I'm going from 0 to +2. What's happening? Am I gaining electrons? Because electrons are negatively charged. So if you're gaining them, that means that you become negative. I'm losing electrons. Okay, how many electrons am I losing? I'm losing 2 electrons. Okay, now look at silver. Silver starts off at, what is the charge over here? What is it starting off? What is its charge with? It's going to be a +1. Okay, and it's becoming an element of silver, which we know is what charge? Silver is 1, the element. When it's all by itself. What did we say about all elements? What charge do they have on them? They're neutral. So then that means neutral means what again? No charge, so it's 0, right? So if I'm going from a +1 to 0, what am I adding? I'm adding a minus, which means I'm adding a neutron. I thought neutrons were
Electron, right?
electrons. Okay, so that means I'm gaining an electron. So silver is being reduced and copper is being oxidized. Okay, so I would copper. Then I type in oxidized. And then silver is being reduced. Okay, that makes sense? Okay, ready to move forward?
Yeah.
Okay. Next thing that we have is called the double replacement reaction, or double displacement reaction, or I like to call it the Swinner's reaction. Do you guys know what Swinner's are? Swinner's. What do you mean by people? Come on, explain. Don't be shy. We're all adults here, right? 2 couples that sleep with other couples, right? So have you guys ever gone to a party where a couple came there together and then another couple came together and then they kind of split up and went their separate ways, right? So that's what happens here. So you're going to be switching partners. Okay. So here A is going to hook up with Y, X is going to hook up with B. Okay. So they're going to be switching their partners. Okay. So that's exactly what happens in a double replacement reaction. You're switching the partners. Okay. So then you're going to get AY and BX. So again, this is called a double replacement reaction. So this usually results in either a precipitation, or you can get a gas formation, or some type of product that you're going to get out of it, right? That is going to be tangible.
Do the Since it's AX and BY, you can choose the AYBX is the second one.
So like, for instance, let's say if A is a metal and X is a non-metal, and then B is a metal and Y is a non-metal. So it's always going to be A is going to hook up with that non-metal. Okay, does that make sense?
Oh.
Yeah.
So then they're non-metal charged.
That's right. Yeah, so you're switching out a metal for a metal. Yeah, exactly. Okay, did you guys get that? Okay, here's your example. Silver chloride precipitates when solutions of sodium chloride and silver nitrate are combined. Write the equation for the reaction.
Is it even 30 seconds? No.
Okay, so what are the reactants? Okay, are you sure? As it says, silver chloride precipitates when. So precipitates means that it forms a solid. It says when solutions of sodium chloride and silver nitrate are combined. So who are going to be my reactants? Sodium, when you said Na, what is NaCl? You said AQ, that's right. Plus
AG.
AG. And agree. AQ. And we're making silver chloride, and what would be the
NA and nitrate.
so NaNO3, and you said silver chloride. What is the symbol for silver chloride? And you said all right.
HCl.
HCl. And it's a precipitate, so that means it's going to form a solid. Right? So I'll put, what is the symbol for solid? Okay. Now, anything that's with nitrate, if it started out aqueous, it's always going to end up aqueous. Because nitrate never likes to precipitate. Yeah, you're because you only give the options. You can't add anything extra, right?
Yeah, like if I were to throw that out myself, I would just put.
Yeah, but you know, by default, you have to have something else, right? Because it's a double replacement reaction. It can't just disappear, right?
Yeah.
Right. So what you put in, you've got to get out. So you've got to account for it, right? Does that make sense?
Does it matter where you put something? I put HCl in front.
That's right. Yeah, doesn't matter. Okay, is it balanced? Yes, it is. Okay, do you guys get that? So his question was, so it only told me that I had silver chloride precipitate. So how do I know that I need to put the sodium nitrate? And the answer is that because you know what you put in, you've got to get out. And you have to account for it. Yeah, they're usually the ones that are going to come together. Yeah. And we'll explain to you what really happens later on, but you need to kind of get this first. So don't worry about it. There's some more layers. Okay. Questions, concerns, Cash? Okay. So another special type of a double replacement reaction is a neutralization reaction. So basically, you have an acid and a base, and it's going to make salt and water. Okay. So you guys already know what an acid. Acid basically has that H plus that's going to be added on to ion, and then a base is going to have the hydroxide. Okay. So this is a very general, very general, it's called the Arrhenius definition, okay, of an acid and base, okay. So here is an example of an acid. So it's hydrogen, and then that's either our non-metal or our polyatomic ion, okay. And then here we have a metal with the OH, okay. So at the end of the day, we're going to end up with water and a salt. Okay, so let me give you an example. So if I have sodium chloride, sodium hydroxide, solution reacting with hydrochloric acid. What will be the products? Again, it's a double replacement reaction. Just treat it like that, and you should be able to figure out what's going to be on the other side. Okay, my reactants. Okay, so what is the symbol for hydrochloric acid? HCl. Anything else I need to add to that? And OH. And what do I need to add to that? Let's see. AQ. Okay, so if it's a double replacement reaction, the H is going to hook up with what? Sure. Hook up with the OH. Okay, so then we're going to get instead H2O. That's solid, liquid, or gas. And NaCl. Okay. Questions? Concerns? Balanced.
How do we know what's?
Because metals are going to replace metals, right? And then, or hydrogen, right? And then non-metals are going to replace other non-metals. So if you have polyatomics, your polyatomics are going to replace each other.
That's probably something.
That's right. It's going to replace this. Okay, so write the equation for the reaction between sulfuric acid and solid aluminum hydroxide. Okay, ready? Okay, what is the chemical formula for sulfuric acid? SO4. Anything else that we need to add to that? Say plus Al what? ALOH. Sure. There should be parentheses, and how many should we have with the OHs? Have 3 of them, right? And that's solid, liquid, gas, or aqueous. Okay, so then what are we gonna get on the other side? You said HOH, and that's what? What is HOH? Oh, it's H2O, that's right. So HOH is the same thing as H2O. That's gonna be solid, liquid, gas, or aqueous. Liquid. Okay, and what else we get? Al2. Parentheses SO4. What? That? AQ, are we missing anything else? Should be 3. Okay, is that balanced? No. Okay, how many aluminums do we have? How many SO4s do we have? Okay. How many H's do we have? Three and 2. Are you sure? 5. And then we have 2. And then the remaining is going to be oxygens, but we can't count the ones here. So just the oxygens that we're putting over here. 3. And the oxygen. Okay, so how can I balance it? Okay, so how can I get my sulfate balance? So I have 3 over here and I have 1 over here. So what can I do?
I had 3
3 where?
in the beginning.
Right here. Okay, so then that gives me 3 sulfates. How many hydrogens do I have now? 6 plus 3. So that's a total of 9. Okay. What about my aluminums? And oxygens, we have aluminum. How can I get my aluminum balance? So put 2 here. Okay. 2 aluminum. That gives me, now we have 12 hydrogens. And then just these oxygens here. So that's a total of 6 oxygens. Okay, so how can I balance my hydrogens.
So, I have the H2.
6 in front of the H2O. That gives me 12 hydrogens. And then 6 oxygens that are not in the circuit. That balanced? Yes.
So, write that one out. I guess I was looking at the last one. Just like, just picking H2O. Just
Anytime that you have an acid
here.
and a base, you're always going to get water. Water is always going to be one of your products. Okay. How are you guys feeling? Good. You feel so good you're putting your hair, right? Okay, good. So let me add on one more type of reaction. Okay, that is not linear. Can everybody got this down? I'll let you know. Everybody, let me know if you once you got it. Was there any other questions that you had? Anybody have any other questions? Okay, good. Okay, so the last one is the combustion reaction. So a combustion reaction, if you have a combustion of a hydrocarbon, hydrocarbon basically means hydrogen and carbon. So that's CH4. It always is going to require oxygen. So if you get a statement that says methane, this is methane, burns with, or is burning, right? That means oxygen has to be present. So the only way that you're going to get fire is if there's oxygen. You're always going to get carbon dioxide, 2. So combustion is going to require oxygen to be present. Okay. So you're always going to have some O2. Usually that's from the atmosphere. You have oxygen in the atmosphere, that was going to get there. So if a building catches on fire, as long as there's oxygen present, it's going to continue to burn. Beautiful. Okay, this is balanced. So then how would I balance it? On that, my girlfriend said, I gave him one harder than this one, but got stuck on this one at first. Too many overs. Say 2 in front of the.
Oh. Unless there's one.
Okay, so 1, 4. 1, 3. Okay. So when you say put a 2 here. So then that would give 4 and then 4. Okay, questions, concerns, cash? So now you should be able to identify the types of reactions by the flavors, right? I like to put those questions on. Okay. So this is just a summary of all the reactions except for the combustion. Okay. Okay, so let's go ahead and take a 15-minute break. I will see you guys back here in 15 minutes. Okay, so we're starting on chapter 11. You guys ready? Okay, so electromagnetic radiation. So this is just going to be energy in the form of electric and magnetic waves. So we have, you guys already talked about it. We talked about gamma rays. What things are gamma rays? Talked about nuclear chemistry. So we have X-rays, we have UV, ultraviolet, we have visible light, we have infrared light, we have microwaves, we have radio waves. All of that is form of energy. And the thing is that it's going to be in the wave. So one thing that they determined about light has what they have. It has a dual property. It acts like a molecule or like a particle, right? And then it also acts like a wave. So it has both of those properties that they exist. So we have to understand what a wave looks like. How many of you guys have been to the beach? So you guys have seen the waves as the wave comes in and everything like that, right? So that's exactly what we're talking about, is a wave, right? Now, if we look at a wave is going to be made up of, and I'm going to show you the camera here. Okay, so we have three waves here, right? What are the difference between those three waves?
The sizes.
The frequency.
Okay.
So,
We can check with that.
no, you're right on both. So frequency basically means, let's say this is our frequency. So we have a little marker, right? So if we look at it, right here, we have this marker. Count the number of complete waves at 5. So 1, 2, that's almost there, right? So here, that's 1, that's 2, that's 3, that's 4, that's 5, that's 6, that's 7, right? So 7 came through, we had almost 3 here. Then if we go here, that's 1. So really rough. Okay. Where I'm saying from this point to that point. Okay, so that would be single. Okay, so this are the cycles, or what we call the frequency. Okay. The point here, or we can say from trough to trough, or peak to peak, right? You guys see that really high. Trough to trough. You can work on a farm. That's a farm, yeah, farm. So you don't want to talk, right? That's right. It has the food or the water for cows, pigs, whatever they're eating, right? And so trough, because it goes up. So trough to trough is just bottom to bottom. Peak to peak is like top. Okay, so that's going to be the distance of a wave, right? And that's going to be called, it's going to be called the wave. Okay. So you can measure the wavelength from peak to peak or trough to trough. Or if you're fancy, you can go. So that would be considered a single wave. Okay. So the wavelength. Now, if you guys look at the wavelength between A, B, and C, which one has the largest wavelength? C has the largest wavelength. Okay. Which one has the smallest wavelength? B has the smallest wavelength. Which one has the highest frequency? Which one has the smallest frequency? Okay, so if we look at the speed of light, C equals lambda. Lambda, the wavelength, nu. Nu equals our frequency. Nu is it's a funny looking V. These are Greek letters. Lambda is a Greek letter. Nu is a like I have new shoes, and it's spelled in right? Lambda is spelled lamb. Okay, so lambda represents the wavelength and nu represents the frequency. These guys, are they directly proportional or are they indirectly proportional? Sure. Are you sure you're gonna put money on it? Do you guys want to bet each other? Okay, now, what did we say? You told me that C had the largest wavelength, right? What is its frequency? Is it larger or is it smaller? Let's say smaller, right? Okay. B has the largest frequency, but it has the smallest wavelength. So would that be directly proportional or would that be indirectly proportional? Indirectly, because they're going opposite directions, right? Okay, so we know by these guys being on the same side, multiplied by each other, they're going to be indirectly proportional. C represents the speed of light. Okay, so when we're talking about electromagnetic waves, regardless of what type of electromagnetic wave it is a form of light. Okay, you guys got that? It is a form of light. So if we're talking about gamma rays, well, gamma is going to be a form of light. It's going to be part of it. So, but we know that the frequency for gamma rays is going to be different than it is for, say, radio waves. Okay, let me give you an example. Did everybody get this down? Or you guys are looking at me like I said something bad? Question? Sure.
So it's
Okay.
1/7, like underneath the waves?
Yeah.
So it's a 1/7
So-
and then what's the top one?
Yeah, it's roughly, these are estimates, right? So, and you can see my line is a draw straight, so it's a rough estimate. I'm saying this is about one wave, right? One wave, so that's one frequency,
Okay.
okay? So here, this one has 7 waves that are going through.
Oh, okay.
This
That
one
was
has
3?
3.
Okay.
Yeah, it kind of sucks. You guys can't see it on the other side of the video.
Right.
Okay. So. Okay, so you guys take a look at it, right? So our gamma rays, this is the Greek symbol for gamma. Our gamma rays, they're going to have a very high frequency, right? So in other words, their wavelength is going to be small, okay? So if we have a wavelength of, say, lambda, lambda equals 10 to the minus 60. And then that's going to be As its distance, right? Okay, now speed of light is C equals the speed of light. Which is going to equal 3.00 times 10 to the 8 meters. So that basically means light travels 3.00 times 10 to the 8 meters per second. Kind of like you guys travel from, let's say, Lemoore to here, driving like 60 miles per hour, right? Similar. Although it's much faster, right? Where did I get this from? It's given. It's a constant. It's always going to be. Okay, so the speed of light is always going to be constant. Always. Okay, now gamma rays. We have a gamma ray that has a wavelength of this. So if we know the wavelength, we can calculate the frequency because the speed of light is going to be equal to lambda mu, right? It was the frequency. So if we change our equation around from mu by both sides by lambda c lambda equals mu. So then we know the speed of light is 3.00 times 10 to the 8 meters per second. We know that our wavelength for our gamma rays is 10 to the minus 6 meters. So meters are not. And so then we're going to get 0.00 times. So, very small wavelength, very high frequency. You want to check that? Questions?
Oh, no, it cut off on us.
It cut off. Sure. Okay, so let me just rewrite it. It's 1/7. Okay. Let me rewrite it because I can't see.
I know, we don't like it.
Okay, so when we're doing exponents, right? So if you have something that's base 10, you have exponents that are exactly the same. This is just basically saying 3.00 times 10 to the 8, right? So this is divided by, right, 10 to the minus 16, right? So if it's divided by something, that means you reverse the sign and you add it to the exponent that is the same base as this. So, yeah, so if I had 10 to the third divided by 10 to the ninth, right? Then I flip. So this is the same thing as saying 10 1 over 9 plus. That's right, because it's a base.
Oh, I see it.
That's right. So if you actually plug into your calculator, right, you should get 3.00 times 10 to the Okay. How do you do that? I'm struggling right now.
How much do they give you in a bottle?
Back. So in this case, that's like I'm saying 5.
Okay. Oh, yeah. We've only ever done it here.
It's like,
I'm saying
which is fun, we're so used to it. I'm telling you, I about this stuff. 18 an hour.
oh, that's good.
No, I love that.
Oh, yeah. That's,
I was at the 360 hours.
Jeez.
And then do
It
your
is
tax on
so
there.
it's like, that means,
Sure, I don't even get half.
yeah, it means that.
Because you're on a thousand, like, you guys have Chem, I'm not equal. I want to do mine.
Everybody got it? Okay. How are you guys doing so far?
Wow.
Wonder.
I feel like you clear it.
Can we get another?
Of course. Okay, so now what I want you guys to do is, let's say we have, somebody give me the wavelength. I know it's kind of hard, you guys use your magnifying glass, but the wavelength for long radio waves.
It's like 2 months. Sorry.
We have a wavelength for long radio waves. Okay, so what? 2 meters. Down there, yes, got it. Okay, let me put it on. I can. Okay, so if you guys take a look, let's say we're talking about long radio waves. So this is 10 to the 4th, right? 10 to the 4th, that'll work for us? Okay, so that basically means 10 to the 4th meters, right?
Okay.
That's pretty long, right? So, because 10 to the 3rd is 1,000, 10 to the 4th is 10,000. So that's 10,000 meters, okay? So if our lambda equals 10 to the 4th, meters. What is our wavelength? Okay. I know, it'd be nice if I could have the image and put this next to it.
I know.
Limited, I'm very limited. Okay, so. So speed of light is. What? Speed of light,
Go, honey. Say it.
hey, that's always gonna be constant, right?
Yeah.
So it's always gonna be constant, so we're always gonna use that. So. One thing that we're changing is our lambda. Our lambda is now 10 to the 4 meters. So in this case, since this is a positive value, we're flipping it up on top. So that's 10 to the 8 minus 4. So then that's going to be 3.00 times 10 to the 4. Glad does that help? Okay, so
I see where you have, so C would be the speed of light. So how are we moving it?
I'm sorry.
So like we have it versus.
1 over S?
Putting the speed of light.
Yeah. So because the equation is C
What was the
equals
whole
lambda, right? So if I multiply both sides, I mean divide by both sides by lambda, right? Then I get u
Because
all by
it's
itself.
it cancels out the.
That's right. So the frequency equals
It would be the S on the bottom.
3.00 times 10 to the 4
0.00.
per second. Now, 1 over second is the same thing as hertz. So you'll see it both ways. Okay, so 1 hertz is equal to 1 over second. Okay,
Here. 1 over what? What is it?
1. So 1 over 1 second is the
Oh,
same
second,
thing as
not
1
7.
hertz. Hertz is
Oh,
spelled HR, like the company, right? The cars. So. And the abbreviation is H. Okay. So that's frequency. Okay.
That is a lot.
So that's a lot.
That's a lot.
So
Wait, wouldn't it be?
frequency though? So what if you're given a frequency?
What do you mean by what do we use?
Because it's on the bottom and the top from 3.0 times 10 over of 8. And bottom is 10 of power 4.
Put it in your calculator.
I know what you're saying. Yeah. So, what would it say for? Figure it out. Wait, didn't we do this in math before when you were like, was yours just something? What's left? I think that's what it is. Just calculate them. So it'd be 3.00 times another 80. Yeah.
Did you get the same answer?
Yeah, I think you need more parentheses. Yeah, I got that.
that.
Oh, yes, there you go.
Fourth?
Which is the same thing as.
Oh, yeah, because you put the zero there and then still be four. Yeah. Okay. That's what you get.
Yeah,
Yeah,
so
that's what I
we're
got. But then you have
Oh,
to
yeah.
turn it into the,
Scientific notation.
Oh, so we did the right.
yeah, you put it in right. We just change it. Oh, okay.
Okay.
So much first.
I just thought like we would like divide each other.
That's what I was thinking.
So when you have the exponent, since they're the same base, all you have to do is subtract it.
Oh,
Subtract, since it's being divided, you subtract it. If it's multiplied, you're gonna be adding.
okay.
Right? Since they have the same base, they're
Right.
both bases.
Why do you understand?
I know.
I don't know.
It's like
Like
so
she
much.
can-
Things like that just, it just sits up there, you know.
We talk about it in nothing.
So you have a doctorate in chemistry or?
I have a doctorate in genetics.
Dang.
Chemistry is fun.
Chemistry's fun.
And then so would
The
it be
last
10,
one.
10 to the power of 4, 1s?
Yeah, 1/s, yeah. Or hertz. You could say hertz. Okay, so it's starting to take a little bit. Let's try one more. Now, the speed, light, the visible light, this light, white light is basically made up of all these different colors, right? That's what makes white light, white light. It's everything added together. And okay, so visible light, which is white light, right? White light has blue light, it has green light, it has yellow light, it has red light, all of that's here. Now, each of those are at different wavelengths. The blue light is at a different wavelength, the red light is at a different wavelength. Okay, now typically when we talk about the wavelength of light and taking colors, so for instance, blue light is going to be about 400. Okay, so 400 nanometers. Okay, so if we have a wavelength of 400 nanometers, what would be the frequency? So now we have 400 nanometers. Okay.
Want your, like, there's 4 zeros. You want your decimal. The decimal start here.
You guys mind if I just, wait, I'll keep one up here.
And then that's 2 zeros like always. Oh, that sounds like.
Got it? Okay, first thing that we want to do is do what? Now, this is nanometers and not meters. So we want to- Right. So How many nanometers would you be? How many nanometers would be in? How many nanometers? 10 to the 9 nanometers. Both ends, right? Okay. So. Send. We want to have. Right, because what that's grabbing the.
Like to the other, like to the.
Yes, but I would say convert this first, make yourself see for yourself, right? So then that would be 4. 0, 0 times 10 to the minus 7. Right? So that's what you're gonna have at the bottom, so it's gonna be. 5 by 4 times 7 meters. Meters are out. So. So what is 3 divided by 3?
Put it up here.
Was that?
Put it on the.
Oh, sorry. Like, you're not even liking it. You know? Sorry. That help? Right, sorry about that.
I like.
How many centigrade should I have? And then the units are?
Oh, wait.
Same thing, no, it's 1 over seconds.
Okay.
Okay, questions? Concerns?
Where do you get the 7 from?
Where did I get the 7
He
from?
did a conversion on the bottom. But is that a 9? But is that a 9? So 10, 9. And then?
Yeah, so 10 to the 9, multiplying that by, so just that bottom part.
Oh.
And I recommend, again, want to make sure that you use the ratio. Meters, it needs to be meters. Nanometers, it will be nanometers.
No, so I think it's like to get to get the one by itself. One
It's-
meter, right?
Okay. Questions?
The what? The 1 end. The 1 end.
So, any other questions? Okay, so now let's change the question. So let's say we're given frequency. Let's say we have 3.25 hertz. What is our weight?
Yeah. Is it for the top one? 3.2.
All the other stuff. Get out of your way. Distracted. Maybe you guys started to practice this. Didn't show up? I don't think so. Yeah, it was meant to be posted. Did you post it?
Yeah. I thought.
But that's all right, no, no,
I thought I
that-
never asked it.
That's all right, it's fine, because I only get it.
I saw it was both published and I was like, did I do that?
No, that wasn't you, that was, yeah, I did, yeah. I had it published. Giving them an extra, a little extra there. So they can- You got to change. what we're
Oh, really?
gonna cover. So we only have Tuesday.
Are you gonna go over here?
Yeah, I am. Not on Monday. Just Tuesday.
Okay.
I forgot about the 4th of July. Like, oh, you guys were gonna have so 3 lectures. Monday. Then Tuesday. Actually, no. Awesome. Okay, you guys ready? So how would I do this? Okay, so we're gonna divide both sides by you.
I agree.
You like?
I get it. That's not it.
Okay. Okay. So how will we determine the wavelength? So what we would do is look at that chart. I'll print out a big one for you guys, so you guys, I mean, because I know it's really hard to see, so I'll print out a big one for you. So now we have a wavelength down here, so we fall into X. Would it be X gamma?
Anything past that.
Yeah. Okay. So we're having a dispute, we have 17, 18. So we need to subtract. So that's negative 17, but this is a smaller value. So then that would be 3.005. 9.923, right? And then if you take times 10 to the 25, it'd be 5. So that's 17, right? Negative 17. Plus 9 to 3. Negative 17. But
Oh, no, it's because I put this.
oh, sorry, you guys, I'll flip it again. I'm gonna be really skinny by the end of next year, running back and forth. I didn't expect to get exercise in class. I know. Yeah, this one here?
Yeah.
We've been talking about that, because I wanted to put it on a swivel, so then I could slide it over or push it down. Yeah. But now that you mentioned that, I would say my students have made a comment, you know.
There you go. You're welcome.
They don't want to listen. Yeah, it's not a good size, especially since it's in the center of the damn classroom. Right? You assume that they would have the camera, so it's like, oh, you can't look right here. I mean, I push to see if I can. Okay. Questions? You guys see how that works?
Yeah.
Okay, let's see if we can add some more layers. Okay. Now, this is energy. So we need a way of converting to energy. The way that we convert to energy is that we use Planck's constant, H. So there's this guy named Planck. It's named after him. He has this constant. I never remember it. So I'll give it to you guys, and you guys can write it on your periodic table sheet as one of those things. The Planck's constant is going to equal 6.6. Is that showing?
Oh, yeah, no. It's weird.
Whoa, that is weird.
6.626.
Yeah, let me see if I can fix that. Hold on.
Negative 34.
Okay. So let me take a picture of this. That's the problem.
Yeah, yeah, and a computer too. Show her like.
Oh, yeah. Okay, let me write it somewhere else. It looks like that. The part is going to be a blackout spot. So.
Yeah. What? 3.200 over 3.2. 0.92 times 10 over 8. Yeah. I see that's what is pushing out again. Yeah. I want to see that. Sure. Okay.
So. Can you guys see it over there? It's showing up on the side.
Um,
Sorry, I can't use that corner. Okay, now, energy is going to equal Planck's constant times the frequency. Now, this is for one photon, okay? So if we get one photon, one energy bundle, one energy light bundle, that's going to be it. So energy is going to equal Planck's constant times 50. Okay, so if we have a frequency, this is our frequency, then we just multiply it by Planck's constant. 6.626 times 10⁴ times frequency, which is 5 hertz, which is seconds. So seconds are gonna cancel out. Somebody do all the heavy lifting. Like it's very kind of- So for your exam, if you have a question like this, I will provide you the equations for provide this and the new, and then I'll also provide you with the equation for energy. And I will also, as I said, you guys can write this on your taking it sheet. That's good. So if you guys want to, you can actually write the equations on your sheets right now. So you write them on your. Then I don't have to come out. Okay. Questions? Concerns? Okay, DJ, you're smiling.
I get this part, this part.
Straightforward, right? Just plug and check, right? The other one's kind of plug and check too. Just manipulate the equation. Okay,
Is it multiplying?
it is multiplying.
Okay.
What's that? No, I was waiting for somebody to plug it into a calculator.
I got 2.15.
So 2.1.
Yeah, 2.1535.
2.1.
So what?
Times 10 to the
10 to the -8. -8, yeah. 5.
5.
Did I say 1.5?
How many significations should I have?
3. I mean 3. 1.5.
Okay, questions? Concerns? Cash? You guys are gonna do a little bit harder?
No.
You okay like this? Okay, and again, this would be for one photon. If we're talking about a whole bunch, we have to take into consideration. So you multiply that by the number. that you have. Okay, so if I told you you had a mole of them. If I told you you had a mole of it, mole of photons, what would I be multiplying by? It's a mole. What's the tattoo on your butt? What is a mole equal? 6.022 times 10 to the 23rd, right?
Yep.
So you multiply by that. If we wanted to know how many or more. Okay? Okay, so let's move on to the next topic.
Wait, so E equals a photon?
What was that?
E is a photon?
E would be, that would be the energy. No, E is energy, right?
E is
It's the
energy?
Energy for a photon. Let me write that down. E is energy. So this would give us the energy for one photon of light at that frequency.
Okay.
Okay. Okay, so back to lecture. Try to get as much in as we can. Okay, so you guys are feeling comfortable with the electromagnetic spectrum. Now, spectrum basically means that it's continuous, right? So it's going from this end all the way down to the other, and they're overlapping, right? So you kind of take a look at this, like for instance, the visible light. It's kind of like the colors of the rainbow. You guys seen the rainbow, right? You don't see separated lines. It kind of just blurs into each other, right? Okay. So, continuous spectrum, that whole band of those colors blending in together. We also will have a line spectrum. A line spectrum is a little bit different. Line spectrum means that you have that discrete lines. So you get that separation. Now, when we talk about chemicals, because chemicals are very unique, they're going to have unique properties. So each chemical is going to have a different line spectrum that they're going to be associated with. So they're going to have a different pattern of lines that you can see, visible lights, or a different pattern of the electromagnetic spectrum. Okay. So we already talked about the wave particle duality. It's like a wave, it's also like a particle. Okay. We already talked about what a wave is. Okay, the other thing that I did talk to you guys about, the height of it is called the amplitude. Okay, this is the height of the wave. Like, so this is the midline. How high it goes up would be the amplitude. Okay, so this is white light. If we put it through a prism, this is what it actually looks like. It separates all of the different colors. Right? And you guys are going to see that later. So if we have a particular element, in this case hydrogen, it has very discrete lines, right? So it has a discrete line spectrum, and it's going to be unique for hydrogen. Hydrogen is not going to look like nitrogen. Nitrogen is not going to look like argon. They're going to be very discrete because what we're doing is we're exciting electrons. Hydrogen only has one electron to excite, and it can be excited at different energy levels. I'll show you that here in a second. Okay, so this is just basically showing us that this is hydrogen. This is the line spectrum for hydrogen. This is the line spectrum for mercury. This is the line spectrum for neon. Quite different from each other. Right? You should be able to distinguish between them. Okay, so there's this guy named Bohr. He basically came up with the idea of how the hydrogen atom behaves and how it orbits, how the electrons orbit around the nucleus. And he said that, you know, this energy level, those electrons, they go to different energy states, right? They can be excited to different energy states. So you can put energy in, it will excite that one electron and push it out to another energy level. This energy level is quantized, meaning that it's in steps. Okay, so if you guys look on your periodic table, on the side are the periods. That represents those different energy levels. Okay, so the numbers on the side of your periodic table. Right here. Yep.
Oh.
Your periods. Remember your periods? Your periods represents the different energy levels. That's what they represent. Yes, you had a question. Okay. Okay, so this is just a cartoon showing you basically. So this is the example of it being continuous, right? A continuous spectrum. This is an example of it being quantized. Quantized basically means you have those steps. Okay, so continuous and steps of energy. So those periods represent steps of energy. Okay, so Bohr basically said, this is the nucleus. This would be that very first energy level. This would be the second energy level. This would be the third energy level. This would be the fourth energy level. Now, when the electron is at ground state, meaning that it's not excited, it's normal, not excited at all, it's at that first energy level. But at any point, we can put enough energy in to excite it to any energy level. Right? Okay, now, how many of you guys have kids or have nieces and nephews or anything like that? Okay, so if I feed them a whole bunch of candy on Halloween, what happens? Was that they get hyper, right? But then what happens at the end of the night?
They crash.
They crash, right? So that's the same thing that happens with the electron. You put energy in, it's kind of like feeding those kids candy, right? Put a whole bunch of energy in, they're gonna be hyper. Rah, they're gonna pop up, right? They're gonna go to that highest energy level, right? And then at the end of the night, they're gonna crash, right? So the electron does exactly the same thing. It goes up to that energy level and then it crashes. When it crashes, it let loose photons. It lets loose the energy that it accumulated to get to that point. And those photons, depending on the frequency of it, will have a different color associated with it. So if we're talking about hydrogen, you saw like 4 different lines, right? We had a blue one, we had a, if you guys look back at it, there's like 4 different lines, right? Each of those represents a different energy level that one electron, that single electron, has been excited to. But since we have so many different atoms of hydrogen or molecules of hydrogen, each one is gonna, you're gonna get one that goes here, one that goes there, depending on the energy that you put in. Right? You guys understand that so far? Show you another figure, they'll help pull it together. Okay. So that movement from that ground state energy level to that higher state energy level is called a quantum. Right? So in theory, the theory is that if we put enough energy in you can actually transport from here to fire, right? Like this. But we have to do every part of your body, every atom, every molecule of your body has to have the right amount of energy, the right frequency to sit there and transport you to fireball. Okay. Yes, they did talk about that. And good job. See, Marvel is great. You learn a lot, right? Marvel is the reason I got into science, actually. Marvel comics. No crap. Okay. So again, the electron is going to start off at ground state and it's going to be excited. Okay. So this is just basically showing you that. Ground state. Then we put energy into it. It gets excited to an energy level. And then it has to drop back down to ground state. When it drops back down to ground state, it lets loose that energy. And it emits light. It emits energy. Okay. You guys are with me so far? Okay, so Bohr is considered to be the father of quantum mechanics or quantum numbers, right? So in the case of quantum mechanics or quantum, the quantum theory, basically it's based upon electrons, right? Electrons being excited at different energy levels, or just knowing where electrons are supposed to be. So every electron in an atom has a specific address. That specific address is composed of what we call 4 quantum numbers. That gives it its specific address. You guys won't need to know all of it, but you're going to need to know a little bit of it. Okay. So we're going to talk about the 4 quantum numbers. The very first quantum number is the principal quantum number. The principal quantum number is just the period. Okay. So if you guys take a look at your periodic table. Okay, we have the periods on the side. So the very first principal quantum number is the periods. So for instance, hydrogen has 1 electron. It's in that very first period. So its very first principal number would be 1. Okay. Now, lithium has 3 electrons. It has 2 of them that will be in the first period, And then it has one that will be in the second period. Right, so then you go 1, 2, 3 electrons, right? Because it's the same number of protons. Right? So 2 of them are going to be in that first period, and then you're going to have 1 that's going to be in the second period. So only 1 of them is going to be in that second energy level, but there's a total of 3. You guys get that? Okay. So if we have potassium, potassium has how many electrons? 19. It has 19 because it has the same number of protons, right? Okay, so how many of them are going to be in the first energy level? 2, right? 1, 2. How many are going to be in the second energy level? 8. 1, 2, 3, 4, 5, 6, 7, 8. How many are going to be in the third energy level? 8. And then how many are going to be in the fourth energy level? 1. Okay.
Okay.
Okay. So you're literally counting each and every electron. It has to occupy the space. Okay. Okay. So first quantum number called the principal quantum number or principal energy level, right? The second one is called the sublevel. Okay, now we have, as of today, we have 4 that officially existed, but we can get more, and I'll explain to you how we get more in a second. Okay, so let me tell you the 4 sublevels. So we have S, the P, the D, and the F. Okay, now the S sublevel has what we call 1 orbital. Now an orbital is kind of like a 2-seater. You don't have a 2-seater, what is it called? A love seat, right? You guys know what love seats are? The little couch that only sits 2 people comfortably, right? If you're big buddy, yeah, 1 person, but normally it sits 2 people, right? Because you want to snuggle with your honey, right? When you're watching movies. Yeah, excuse me. Okay, so now the orbital is kind of like a love seat, right? It can technically hold 2 people, right? So an orbital can hold 2 electrons. S sublevel has 1 orbital. The P sublevel has 3 orbitals. The D sublevel has 5 orbitals. The F sublevel has 7. Okay, you see a trend?
Yeah.
Okay, now what comes after F is G, right? So how many would you expect the G to have?
9.
And H? 11. Okay, now you guys see that trend, okay? Okay. So now an orbital can hold how many electrons? 2 electrons. So then how many orbitals appear? That's right. So how many electrons can the S orbital hold? 2. How many the P holds? How many do the D? the F, the G, and the H. Okay, you guys got that so far?
So the letters are the, what is it, the sublevels?
What was that?
The letters are the sublevels?
The letters are the sublevels. Okay. Questions? Concerns? Cash?
So when we're looking at the video, right?
Mhm.
Like the little numbers on there, they have like 2, 8,
Oh, yeah, we'll get there. You're on the right track. You're exactly right. We'll get there, I promise. Give me 1 second, we'll get there. Okay. So, you go to your periodic table. So if you go to the periodic table, we can break up the periodic table in terms of the sublevels. Okay, so group 1 and group 2, that's going to be our S. Group 13 through group 18, that's going to be our P. Group 3 to group 12, that's going to be our D. And then if we go down to the very bottom, and that's going to be our F.
What's the transition to S?
Okay. Yeah, the P story is going to exclude HE. HE is, yeah, HE is going to be technically on the other side. Yeah, it's going to be on the other side. So helium, in other words, the helium is really pushed over. What was that? Okay, so now what you guys are going to learn real quick, it's called electron configuration. Electron configuration. Okay, now if we have hydrogen, we're talking about just hydrogen. Hydrogen has how many electrons? Hydrogen has 1 electron. So the way that you write its electron configuration, since it only has 1 electron, so you're telling me where that electron is going to be located at. You're saying it has 1 electron, so you write the principal number, the period. The subshell, what subshell would that be? S. And how many that's there? 1. Okay. So that's how we write the electron configuration for hydrogen. Okay. So let's do a harder one. Let's do carbon. Okay. So carbon is over here, right? So in other words, I told you it's like an address for all of the electrons in carbon. Okay. So when we write the electron configuration for carbon, so you always want to start for every electron. The first electron is going to fill up this very first spot. So it's going to be the period. 1. Then you put S. How many electrons can the S orbital hold? Or the S sub? It can hold 2, right? So we put 1s2. Okay, so okay, so then that accounts for these 2 spots, right, that are in that first period. And this. So we take a look. The very first number is the period, right? That 1 represents the period. Okay, so the 1 represents the period. And then the superscript after the S tells me the number of electrons that would be in the S. There would be 2, which is the max it can hold, right? So, but that accounts for the first 2 electrons in carbon. And it continues, we're not done. So if we go, carbon is located in the second period, right? So then we write 2, and then S first. And how many does the S subshell hold?
2.
It can only hold 2. 2s2. Okay, and then we get to carbon, that's 1, 2, 2p. And how many are in the P? 1, 2. Okay, so it's 1s2, 2s2, 2p2. Okay, yeah, see that? Okay, so let's do a harder one. Now, before we do a harder one, let me tell you, you're gonna get mad at me, but I'm just gonna tell you that. But when we get down to the D does something that's a little weird. It drops it down 1. And instead of this being 4, the fourth period, the D is going to call this guy 3D. And then this guy is going to be 4D.
Oh.
Then this is going to be 5D. And this is going to be 6. Okay, so instead of this being the fourth period, when you get to the D, it's going to drop it down to the third period. Okay, so let's do something. Let's do ruthenium 44. So RU.
Oh,
Write down simple RU.
start with S and then work our way down.
You start at the 1s. An S2, right? Then we have 2s. 2. That's right. For every single one. So now here we have 6. That's right. So it's 2p6.
Is that 1s2?
The S2. I'm gonna finish it down here. So 3p6.
4s2.
That's right.
And then 3d.
That's right. Six, 4s2. Then you go 3D, 3D10.
So it'd be 5s2.
No, it goes, now
Oh,
goes
oh, oh.
P, go back to P, but it's 4. Goes back to 4, or
Oh, 'cause
P6,
period 4, 6.
Okay.
or period, yeah.
And now it's 5s2.
Then it's 5s2,
And then 4d.
and it's 4D, 1,
Oh, yeah.
2, 3, 4, 5, 6.
I think I get
Now, the same thing happens with the F. Only thing, the F starts at 4. So this will be 4F. And then this would be 5F. Okay. The other thing about the F subshell is that these last two are really, these two, they're really in the D, right? So they really belong in the spot right here. So do you guys remember when I showed you what the periodic table really looks like, where it spread it out, right? So it just shows us that spot, okay? Okay, questions? Concerns? Screw something up? Okay,
Yeah.
so let's say we have, our element is, let's do atomic number 94. 94. Yes.
Yeah.
Yes.
Like at the bottom of S.
Yeah, but I'm making them work for it first. So atomic number 94. Okay, so you guys gonna walk me through it?
Yeah.
So what is atomic number 94? Yep, it's PU. So we're gonna write down what it is. PU. Didn't I say 94?
Yeah.
So it's PU. Okay. So, all right, somebody say 1s. 1s, what? 1s2. So it starts off at 1s2. Then 2s2. 2p6. 3s2. 3p6. Then it's 4s2. 4s2. 3d10. Then what's after 3d10? 4p. 4p6. And then 5s2. then 40-10. Okay, so 40-10. Okay, and then after 40-10, 5p6. Then 6s2. Okay. And then we go down here because it shoots down to the 4f. So 4f what?
Five to 10. Yeah. That's what I thought.
Or
Yeah,
F.
she's downstairs.
4f. How many can the f hold? No, not 15.
14.
14.
Oh, so it'd be 14.
Oh, we don't count those last two?
Those last two are part of the D.
What?
They're just placeholders for the D.
Oh.
Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. And then we go back up to the D. So back up here now. You said 5D. 5D what? 5D10. Okay. 5D10. Okay, so we got rid of these.
5d10.
And then, what period are we on? 6 period, so 6p6. And then, what's after 6p6?
6p6. Would it be the
7s2.
7s2?
Yep. Okay, 7s2,
And then wouldn't it be 5f?
5f, 5f6. 1, 2, 3, 4, 5, 6. Okay, it's a lot, right?
Yeah.
Are your arms tired?
4f.
Okay, so since we know that it's a lot, what we also know is that once you get to noble gas, you're considered to be stable, right? So if you go to the nearest noble gas from that element, the one that's right before it, so what would be the noble gas that's before P? 86, okay? So radon, right? So then you can also write it by saying Pu, the noble gas that's right before Pu. So we put radon. So we put it bracket Rn. And then we'll just start right afterwards. So then it'll be 7s 2 5f. Okay, so basically what you're saying is you have all the same electrons as radon, and then whatever else is afterwards, right? But you can only use the noble gases. You only use the noble gases. Okay? Exactly, but I wanted you to work for it because then you appreciate it that much more. But still, people will write them all out.
Wait, what's too much?
Okay, do you guys see that?
Plutonium, so when you have the RN, what did you do?
So by using the RN, I'm saying I have all of these electrons that RN has, which is the same thing, right?
Right.
Because- And then I just put 7s, because that would be the next thing that follows it, 7s2, and then 5f6, 5f6.
Okay.
Okay. Okay, so that's electron configuration. So stop right here. We'll pick this back up on Monday, I mean, on Tuesday. Wednesday, no, Tuesday.
Sorry, I'll be about.
We are gonna do a live on Tuesday. Lab 6 is being started. I am. Oh, you're getting partial? I usually do it right after class, so,
I know.
okay.
For what?
I want you guys to take it out.
No. I know, but no, I know. You're just so curious, huh? No. I was.
Yeah. I'll think about the.
Are you the
I'll figure it out. Any other questions? Yeah, the practice test is gonna be adjusted. I don't think we're gonna do that one. We're really close though. We're really close.
It's not
Consider
doing
yourself.
well.
Okay. Everybody's okay? Everybody wants to jump off bridges? We're not allowed. No jumping off bridges. Okay, I will see you guys on Tuesday. You guys have a good work. Study. Get caught up.
Thanks. Where you go? Oh, wait.
So it's like- Guys.
Whether it's always gonna be everything. Yeah.